welcome to the first lecture of module 2, which is on mass transfer coefficients. So, before going to this lecture, let us have a small recap of the module 1 what we have covered. So, in module 1 we have considered the diffusion mass transfer. The diffusion occurs mainly due to the molecular diffusions, and we know how to calculate the flux. And we have also discussed the difference between the molecular transport or molecular diffusion and the convective mass transfer or convective diffusion. In case of convective diffusions, we have seen that the rate of mass transfer is much faster compared to the molecular diffusion, and the reason for higher rate of mass transfer in case of convective mass transfer is due to the bulk motion of the fluid. So, to account how to calculate the flux in case of convective mass transfer, we need to know a simpler method, which is the mass transfer coefficient method. Mass transfer coefficient. So, by this way we can simplify or we can very easily calculate the flux for convective mass transfer. Convective mass transfer occurs due to the bulk motion of the fluid, and the mass transfer is faster compared to the molecular diffusion. So, what are the concepts of mass transfer coefficients? The mass transfer coefficient can be defined the rate of mass transfer. We know rate of mass transfer is proportional to the driving force, concentration driving force. And also the rate of mass transfer is also proportional to the area of contact between the phases. So, if we consider W A is the rate of mass transfer, in kmol per second, then we can write W A is proportional to A into concentration gradient delta C. So, from this we can write W A is equal to K C into A into concentration gradient. This K C is proportionality constant of this equation and is known as the mass transfer coefficient. So, mass transfer coefficient Kc is equal to flux divided by concentration gradient, which is equal to molar flux divided by concentration driving force. In this case, there are other mass transfer coefficient. One is called local mass transfer coefficient. The local mass transfer coefficient we can define by the local flux divided by the local driving force. Local mass transfer coefficient we can write local flux divided by local driving force. And the average mass transfer coefficient can be defined as the ratio of the average flux and the average driving force. Is equal to average flux over a surface and the average driving force. So, there are many type of mass transfer coefficient depending on the situations. In case of mass transfer, we can use concentration as the driving force. We can use partial pressure if it is in the gas phase, partial pressure as the driving force, and we can also use the molar fraction as the driving force, and so on. But in case of heat transfer, only the temperature is the driving force. So, depending on the situation, we can define the mass transfer coefficient. So, on the following basis: mass transfer in the gas or liquid phase, so if it is gas phase, there is gas phase mass transfer coefficient. If it is in the liquid phase, it is liquid phase mass transfer coefficient, and also the choice of driving force. And third one is whether diffusion occurs, diffusion of a particular component through non-diffusing B or equimolar countercurrent diffusion. Counterdiffusion of A and B. So, depending on these situations, we can define the mass transfer coefficients, and as we know, for a particular film thickness delta, the flux we can write as the mass transfer coefficient into the driving force. Let us consider the case of diffusion of A through non-diffusing B. How to calculate the mass transfer coefficient? So, for the case of diffusion of A through non-diffusing B, we can write flux is equal to kg, the gas phase mass transfer coefficient between 2 points if the partial pressure difference is PA1 and PA2, then it is kg PA1 minus PA2 is equal to ky into Ya1 minus Ya2. It is in mole fraction basis, molar fraction, or if in terms of concentration also we can write mass transfer coefficient into Ca1 minus Ca2, say equation 1. This is for the gas phase. For liquid phase, we can write flux is equal to Kx Xa1 minus Xa2 is equal to Kl liquid phase mass transfer coefficient Ca1 in terms of the concentration driving force Ca2. So, this is equation 2, where Kg, Ky and Kc are the gas phase mass transfer coefficient. Here Kx and Kl are the liquid phase mass transfer coefficients. The Ky has the unit like kmol per meter square second into delta y. Delta y is the mole fraction driving force. Now, if we compare for the ideal gas, we can write Ca is equal to Pa by RT, where Pa is the partial pressure of A, and if we consider the thickness between the 2 points is L, we know that the flux equations for diffusion of A through non-diffusing B we have earlier developed. Na is equal to dAB Pt divided by RT L PBLM into Pa1 minus Pa2. PBLM is the log mean pressure difference, which is PB2 minus PB1 divided by ln PB2 by PB1. So, if we compare this equation with equation 1, we can obtain Kg is equal to dAB Pt divided by RT L or delta PBLM KY DAB PT square divided by RT delta PBLM, and Kc is DAB PT by delta PBLM. Similarly, for the liquid phase, the diffusion of A through non-diffusing B, we know that flux equation Na is equal to dAB rho by m average divided by delta XBLM into XA1 minus XA2. So, if we compare this equation with this equation 2, we can obtain, so the relations, this will be say delta. So, we have compared these equations with equation 1 to obtain the correlations of gas phase mass transfer coefficient Kg, Ky and Kc. Now, if we compare these equations for the liquid phase flux with the second equation, we can obtain the correlations between the liquid phase mass transfer coefficients. So, from that we can write Kx is equal to dAB rho by m average divided by delta XBLM, and KL is equal to dAB by delta XBLM. We can relate among the mass transfer coefficient. We can write Kc is RT Kg. So, from this we can clearly see that dAB PT by delta PBLM, this part is Kc. So, the Kc is equal to RT Kg. Similarly, Ky is equal to PT Kg, and Kx we can write rho by m average into Kl. So, the relations between the mass transfer coefficient in the gas phase as well as in the liquid phase. Now, consider another case where equimolar counter diffusion of A and B. If we consider the flux for the gas phase, we can write flux is equal to Kg dash. So, the dash which we distinguish between the equimolar counter diffusion and the diffusion of A through non-diffusing B. So, into pressure driving force PA2 is equal to Ky dash Ya1 minus Ya2 is equal to Kc dash Ca1 minus Ca2. And for the liquid phase, we can write flux is equal to Kx dash Xa1 minus Xa2 is equal to Kl dash Ca1 minus Ca2. So, say this is equation number 3 and this is equation number 4. Now, for equimolar counter diffusion, we know that flux Na is equal to dAB by RT delta PA1 minus PA2. So, if we compare this relation, say X with equation number 3, we could be able to obtain the relations between Kg, Ky and Kc. So, the equation for the gas phase, we obtain Kg dash will be dAB by RT delta and Ky dash is dAB PT by RT delta and Kc dash is equal to dAB by delta. Similarly, for the case of liquid phase, we know that flux, this is for gas phase and this is for liquid phase. Flux is equal to dAB into rho by m average by delta into Xa1 minus Xa2. So, if we compare this equation y with equation 4, we could be obtain the relations between Kx and Kl. So, for liquid phase, Kx dash would be dAB rho by m average divided by delta and Kl dash dAB by delta. So, we could convert between the Kc dash is equal to RT by PT, Ky dash is equal to RT Kg dash. Similarly, Kx dash will be rho by m average into Kl dash is equal to C average into Kl dash. So, this is the conversion. Now, if the concentration terms are defined in terms of mole ratio unit, that means Ya is equal to Ya divided by 1 minus Ya, and that is the mole ratio basis, and to Xa is equal to Xa by 1 minus Xa. If we define this way, the flux equation Na, we can write K capital Y, Ya1 minus Ya2, and in case this is for gas phase, and flux Na is equal to Kx capital X, we can write Xa1 minus Xa2. This is for liquid phase. This is mole ratio unit, that is F free basis. Now, the mass transfer coefficients between the two systems, diffusion of A into non-diffusing B and equimolar counter diffusion of A and B. What are the difference? In case of diffusion of A, into non-diffusing B, the mass transfer coefficients, which are Kg, Ky, Kc, Kx and Kl, these are related with the log mean concentrations of the species. Log mean concentration of the species B, which is non-diffusing. So, the mass transfer in this case depends on PBLM or XBLM. But on the other hand, for the equimolar counter diffusion of A and B, the mass transfer coefficient Kg dash, Ky dash and Kc dash, Kx dash, Kl dash, these are not dependent on log mean concentration difference of species B. This type of mass transfer coefficient is known as Coulomb-Drouin mass transfer coefficient. Coulomb-Drouin mass transfer coefficient. Now, there is another type of mass transfer coefficient, which is F type mass transfer coefficient, and we know earlier we have derived the flux equation Na is equal to Na by Na plus Nb dAb Pt divided by RT delta ln Na divided by Na plus Nb minus Ya2 divided by Na by Na plus Nb minus Ya1. So, this we can write equal to Na by Na plus Nb into F ln Na by Na plus Nb minus Ya2 divided by Na by Na plus Nb minus Ya1. In this case, we can write Ya is equal to Pa by Pt and F is equal to dAb Pt by RT delta. Similarly, for diffusion of A through non-diffusing B, these correlations can be obtained. F is equal to Kg Pb/Lm, and also for equimolar counter diffusion, if we can write Kg dash Pt. This is diffusion of A through non-diffusing B, and this is for equimolar counter diffusion. So, what is the relation between Kg and Ky? We know that for two different points, one and 2, we can write Ya1 Pa1 Pt minus Pa1 and Ya2 Pa2 by Pt minus Pa2. So, the difference Ya1 minus Ya2 will be equal to Pa1 by Pt minus Pa1 minus Pa2 by Pt minus Pa2, which will be equal to Pt into Pa1 minus Pa2 divided by Pb1 into Pb2. So, we can write Pa1 minus Pa2 would be equal to Ya1 minus Ya2 into Pb1 and Pb2, Pb1 Pb2 divided by Pt. Now, we know that flux Na is equal to Kg Pa1 minus Pa2 is equal to dAb Pt by RT delta Pb/Lm into Pa1 minus Pa2 is equal to dAb Pt by RT delta Pb/Lm into Ya1 minus Ya2 into Pb1 Pb2 divided by Pt. So, we know that Na is equal to Ky into Ya1 minus Ya2. So, we can write Ky is equal to dAB Pb1 Pb2 divided by RT delta Pb-Lm. So, we can write Kg into Pb1 Pb2 divided by Pt. Similarly, we can derive the relations between Kg dash and Ky dash. As we know, the relations between Pa1 minus Pa2 is equal to Ya1 minus Ya2 into Pb1 Pb2 by Pt. We can write flux Na is equal to Kg dash Pa1 minus Pa2 is equal to dAB by RT delta and into P partial pressure of A minus partial pressure of at point 1 and at point 2 Pa2 will be equal to dAB by RT delta Ya1 minus Ya2 multiplied by Pb1 Pb2 divided by Pt. And we know that Na is equal to Ky dash into Ya1 minus Ya2. So, we can write Ky is equal to dAB Pb1 and Pb2 divided by RT delta is equal to Kg dash Pb1 Pb2 by Pt. So, similar correlations like Kg and Ky, we can also obtain the relations between Kg dash and Ky dash. Now, the conversion among the gas phase mass transfer coefficients. So, we know F is equal to Kg Pb Lm, and this related with Ky Pb Lm by Pt is equal to Kc Pb Lm by RT, which we can write Kg Pt is equal to Ky dash is equal to Kc dash Pt divided by RT. Similarly, we can get the relations among the liquid phase mass transfer coefficients. So, that is also related with F type mass transfer coefficients, which is equal to Kx xBlm is equal to KL xBlm into concentration is equal to KL dash C is equal to KL dash rho by M is equal to Kx dash. So, these are the relation among the mass transfer coefficient in the gas phase and the liquid phase. So, let us consider an example to calculate the mass transfer coefficients in the gas phase and also the film thickness or the gas film thickness. So, consider a large volume of pure nitrogen gas at atmospheric pressure is flowing over a pool of liquid of methanol, which is evaporating, and nitrogen is assumed to be insoluble in liquid. The gas phase mass transfer coefficient of methanol is given. Assume vapor pressure of methanol at 298 Kelvin is 10 kilopascal. Calculate Ky, K small y, Kc, K capital Y and F. And the second problem is, if the diffusivity of methanol at 298 Kelvin is 2 into 10 to the power minus 5 meter square per second, calculate the thickness of the gas film. Now, let us consider for the first case. This is the case of diffusion of A through non-diffusing B, and given Pt is 1 atmosphere, which is 101.3 kilopascal, R is 0.082 meter cube atmosphere per kmol Kelvin, which is equal to 8.3066 meter cube kilopascal per kmol Kelvin, and T is given 298 Kelvin. Now, K small y is equal to Kg Pt from the conversion equation. So, we can write 2 into 10 to the power minus 5 kmol per meter square second kilopascal into Pt 101.3 kilopascal. So, this will give you 2.03 into 10 to the power minus 3 kmol per meter square second delta y. Similarly, we can calculate Kc, which is Kg RT. So, Kg is 2 into 10 to the power minus 5, R is equal to 8.3066, and temperature is 298 Kelvin. This is meter per second, which is equal to 0.0495 meter per second. Another is K capital Y. So, PA1, the partial pressure at point 1 at the surface is 10 kilopascal. So, PB1 is equal to Pt minus PA1, which is equal to 101.3 minus 10 kilopascal, which is 91.3 kilopascal, and also PA2 is equal to 0. Therefore, PB2 is equal to Pt is equal to 101.3 kilopascal. So Ky capital Y is equal to Kg Pb1 Pb2 by Pt. We have derived this equation. So if we substitute 2 into 10 to the power minus 5, 91.3 into 101.3 divided by 101.3, this is equal to 1.83 into 10 to the power minus 3 kmol per meter square second delta Y. And we know the relations between F and Kg Pb So this is 1, and we can calculate F, which is equal to 2 into 10 to the power minus 5 into Pb2 minus Pb1 by ln Pb2 by Pb1 is equal to 2 into 10 to the power minus 5, 101.3 minus 91.3 by ln 101.3 by 91.3. So this will give the value of 1.92 into 10 to the power minus 3 kmol per meter square second. So to calculate the film thickness, we know Kg is dAb Pt divided by RT delta Pb ln. So delta we can write is equal to dAb Pt divided by RT Kg Pb ln. dAb is given 2 into 10 to the power minus 5 meter square per second. Pt is 1 atmosphere is equal to 101.3 kilopascal, and R is 0.082 meter cube atmosphere per kmol Kelvin is equal to 8.3066 meter cube kilopascal kmol Kelvin. So T is 298 Kelvin. So Kg is equal to 2 into 10 to the power minus 5 kmol per meter square second kilopascal. PBLM we have already calculated 101.3 minus 91.3 ln 101.3 by 91.3 is equal to 96.213. So after substitution, delta will be 0.425 millimeter. So this is the typical film thickness. So the typical values for the mass transfer coefficient and the film thickness in case of the gas phase, Kc is equal to about 10 to the power minus 2 meter square per second, and film thickness delta is approximately 1 millimeter. In case of liquid phase, kl is approximately 10 to the power minus 5 meter square per second, and delta is film thickness is around 0.1 millimeter. So, this is end of lecture 1 of module 2. Thank you.